Welcome back, mineralogy fans. We group minerals by their chemistry, but we identify them by their physical properties. The Minerals Lab on our Earth Explorations notes page, available on iTunes U, has dichotomous keys that are based on these diagnostic physical properties. The first and most basic physical property is its luster, that is, the way light reflects off of or transmits through the specimen. There are two main divisions we are concerned with, which are metallic luster and non-metallic luster. Metallic minerals reflect light well, but do not transmit light at all. We say they are opaque to light. Non-metallic minerals, for our key, is everything else. But for your education, we can describe various non-metallic lusters, such as vitreous or glassy, earthy or dull, pearly, silky, or resinous. The most common mistake beginners make in this first split is thinking a vitreous luster, such as this, in muscovite, is metallic. A close examination shows that a seemingly a metallic mineral like muscovite is actually non-metallic vitreous because light can pass through it. Muscovite has historically been used as window panes, an impossibility for a comparably thin sheet of gold or silver. We now have split off a few metallic luster minerals from the majority of non-metallic minerals. The next step in our dichotomous key is to test the mineral's hardness. The Mohs scale of hardness is a relative scale from 1 to 10, with higher numbers being able to leave a scratch in the surface of softer minerals. The 10 minerals that stand as placeholders for the 10 relative hardness values are, from softest to hardest, talc, gypsum, calcite, fluorite, apatite, feldspar, quartz, topaz, corundum, and diamond. Looking at an absolute scale, which measures hardness in Vickers, which we measure by the indent left after shoving a diamond point into a mineral's surface, we see most minerals have a range of hardness depending on variances in chemistry, and even single mineral grains can have a hardness range depending on if you were scratching it with the grain or against the grain of the atomic structure. Some common minerals we can use to test for hardness are your fingernails, which should be about 2.5 and thus scratch talc or gypsum, but not calcite. A copper penny is 3.5 and will scratch calcite, but not fluorite. A paper clip is around 4.5 and can scratch fluorite, but not apatite. A steel knife is around 5.5 and will scratch apatite, but not feldspar. And being that this is about halfway along the hardness scale, and most useful to divide the minerals, we use a 5.5 as a benchmark. Not only are steel knives 5.5 hardness, so are glass plates you can get online or from your local rock shop. We use the glass plates to test for scratches from a mineral sample, but never hold the glass plate in your hand, as fractured glass and sliced tendons don't make for good field work. It's hard to read your field notes through all that blood. So place the hardness plate down on a flat surface, and then press your mineral in, but give it some force. A feldspar is hardness 6, and so it will barely leave a scratch in the 5.5 hardness glass. If you just give a weak scratch, it's not going to do it, so put a little muscle into it. A mineral softer than 5.5 will not scratch glass, but it might leave a powder streak behind that some people mistake for a scratch. Rub away any powder and then look carefully at the glass and even test it with your fingernail to determine if you have truly scratched the glass. If not, go to the minerals on your key that have less than 5.5 hardness, and then maybe try your fingernail, a penny, or paperclip to hone in. If you do leave a scratch, go to the minerals over 5.5, and with experience you can tell by how deep the glass was scratched what the probable hardness of the mineral is. Only a rare few minerals have over 7.5 hardness. Our next diagnostic property is streak. Some microcrystalline minerals may have more than one color. Due to the size and alignment of their crystals, they may have more than one luster, too. But if we turn the mineral into a powder, it gives a diagnostic color. For this test, we use a porcelain streak plate with a hardness of about 6.5, which means we can't do this test on anything harder than feldspar. If we test a diamond on a streak plate, we end up with porcelain powder, and possibly a fractured diamond as well, as diamonds are brittle, even while being really hard. As with the glass plates, do not hold a streak plate in your hand while using it, but place it on a flat surface first. Most minerals soft enough to leave a streak give a white powder, so when we cover individual minerals I usually only mention streak if it is not white. The next property is the most obvious, color. However, it can also be the most useless, as what I've been showing you while talking about color is all just quartz. Slight impurities can change the color of some minerals drastically, so we must be careful. Nonetheless, some minerals really do take on a single diagnostic color or narrow range of color. If you are colorblind, you will have some added challenges with color and streak. These are tests to help you determine if you are colorblind. If the number that appears in the lower right-hand corner does not match what you are seeing inside the field of colored dots, then you either know you're colorblind or should go get checked out by your eye doctor. The next property is cleavage or fracture. If you break the mineral, does it split along flat cleavage planes or irregular fracture surfaces? If there is cleavage present, does the mineral show 1, 2, 3, or more distinct planes of cleavage? And what angle are they to each other? Not all cleavage is equal, and some is better than others, and some must be found by looking for microsurfaces which all reflect the light at the same time as you turn the specimen in your hand, because all those microsurfaces are parallel to each other along the cleavage plane. The most difficult issue for beginning geologists is telling cleavage from crystal habit, the shape the mineral takes on if allowed to grow into its own form. A crystal may grow with flat faces which have nothing to do with its cleavage planes, or perhaps there is no cleavage at all, only fracture. Quartz crystals are a great example of this, with their hexagonal pyramid crystal habit of flat faces and fracture with no cleavage at all. The best I can give you is to try to know the crystal habits of the common minerals, and if you can, break the mineral and see if it results in cleavage or fracture. If you can't break the mineral, look for fresh faces that look recently broken. If it's a crystal habit, it might look old and worn. If it's a cleavage, it might look a little fresher and newer. So look for the freshest, newest breaks on a recent break. Our key lumps all other characteristics together, and some are more important than others. Specific gravity is the mass of the mineral relative to an equal volume of water. Most minerals have a specific gravity about 2.7. But the metallic minerals are often over 5, which makes them quite distinct when you pick them up, which isn't that spectacular in video, unless I use slow motion video and drop a 7.5 specific gravity galena on my hand. Another common test is to put hydrochloric acid on the mineral and look for a bubbling reaction we call effervescence. This is the diagnostic test for the carbonate minerals. Calcite effervesces vigorously with hydrochloric acid, while dolomite only weakly reacts, and often needs to be turned to surface area rich powder before the reaction becomes evident. Geologists can get very intimate with rocks, after all we date them, and so the feel, taste, and smell can come into play as well. Very soft minerals like graphite or talc can feel like soap when you rub them with your fingers. Halite tastes like salt because it is. And sylvite is used as a salt substitute, but people often complain that it tastes like a bitter salt. We often smell rocks for sulfur or petroleum, and if you ever do a streak test on sphalerite, you'll know it. The zinc sulfide powder smells like rotten eggs. Some minerals have optical properties, such as calcite's double refraction, from which science learned much about optics, or ulexite, which, like fiber optic cables, have total internal reflection which transmits light, and thus an image, from one side of the crystal directly to the other side, the reason that this material is called TV rock. The feldspars display parallel lines called striations. Magnetite is magnetic. and the micas are elastic. Some minerals are radioactive, or triboluminescent, that is, they spark or glow when crushed. One of my favorite physical properties is fluorescence. I love taking my portable shortwave UV out in the field to find fluorescent minerals and, well, the exoskeletons of many scorpions will fluoresce a bright green. Using these physical properties, we can conclusively isolate the various mineral species. To start, you should turn to your dichotomous keys to hone in on the identity of the mineral until it becomes second nature to you. Eventually, the most common minerals will be obvious to you as we proceed from walking through geology to taking a brisk jog. But nature doesn't like to be pigeonholed, and the oddball varieties will sometimes stump even the most seasoned geologist at first. We now turn our attention to using these techniques to explore individual minerals, and we will start with the silicates, which is such a large group we will need to break them into several episodes. When we come back next time, we will look at an organizing principle for silicate minerals, the Bowen's reaction series.